Okay, let me look at a couple of other functions, namely take and drop. So if I take, let me say, 4 elements from the list from 1 to 10, you can probably guess what that does. It gives me the first 4 elements. If I drop 4 elements from that list, it does what you'd expect. If I take more than I am allowed, well, actually nothing goes wrong. But here, if I drop 20 from the list 1 to 10, well, I can only drop the first 10, but it doesn't mind if you try and drop more. Oops, sorry, I've scrolled up by mistake. Oh, sorry, key bindings are a bit funny. Okay, if I try and take more from the list than I should get, then you just get all of them. I can even, sorry, something's happened with my key bindings. If I try and take, let me say, a negative number of elements, you just get the empty list. If I try and drop a negative number, then that's equivalent to dropping nothing at all. Okay. Okay, let's see what these definitions look like. Let's hide them. And we can use them if we want to access them via the path P. Okay, so let's take some number of elements. So what is the type of this thing? Well, it takes a small number, an int, and a list of things, and produces a list of things. Okay, so here we're going to also define by recursion, but the tricky thing here is the base cases are, well, there's, in some senses, more than one base case. So one base case is where the list you're trying to perform an operation on is empty. Because in that case, the only thing you can ever do is return the empty list. You can never create any elements. And this is a function that never crashes. So the only thing you can do with the empty list is return the empty list. Okay, that's one of the base cases. But the other base case is when you're trying to take a number of elements that is 0 or less. And in that case, you return the list unchanged. So this is a function with 2 base cases. So let's take the first of those first. If we're going to take n elements from some list, x's, where n is less than or equal to 0, then what should the answer be? Well, take is a function which, well, here's an example. So it should be the empty list, yeah. In fact, so we don't actually care what x is when in that particular case. Okay. The other base case is when the list itself is empty, and then we don't care what n is. Right? And then the answer is also the empty list. And then finally, if we want to take some number of elements from a list which is necessarily not empty, and this is the classic recursion pattern, where we say, well, let's suppose we know what the answer is to take. Oh, actually, this is a little bit tricky because the recursion is in 2 parameters at the same time. Okay, it doesn't help us to know what it is to take n elements from the list x's, because we don't want to take n elements from x's. How many elements do we want to take from the rest of the list? We want to take n minus 1 elements. So actually the recursive case is recursive in 2 parameters at the same time, namely the numeric parameter and the list parameter. So that's the sub-problem. We take n minus 1 elements from the rest of the list, we get the answer we want by putting the first element on the front. Here we know that n is bigger than 0, and we know the list is not empty, so we know we're definitely going to have x as part of the answer. Okay. Any questions? Okay, let's take drop, which has the same type as take, and it has a very similar definition. The base case here should be rather similar when n is less than or equal to 0. If we want to remove the answer, obtain an answer by taking the list and removing n elements, and the number of elements we want to remove is less than or equal to 0, then what's the answer? A bit louder. The original list, yeah. We return it as it is. If we want to drop from the empty list, well, we can't drop anything from the empty list, so we don't really have any choice what to return in that case. That's just the empty list, the same as the other case. And the final case is similar to the one above. We have a non-empty, we're going to take a non-zero number of elements from a non-empty list. Remember, we're throwing them away and returning what's left, so the answer will be the same as dropping n-1 elements from the rest of the list. Okay, let's just compile that. Okay, any questions? No? Okay. Okay, let's think about how we can test these guys. Let's start with the definition of take on its own. But what kind of properties? Give us an example of a property you might expect from the function take, just to check that we've done the right thing. Anybody?
Get the right amount of elements in this.
The right amount of elements. Okay, so knowing exactly what the right amount of elements is maybe is a bit tricky. So we have take n from a list x's. Then the question is, it's about take n x's. The suggestion was that we should take the right number of elements. So what that means is that the length of this somehow should be right. Okay. Now exactly what is right I'm not so sure about, but let's take a slightly simpler test relating to that. One thing we know for sure is the number of elements you take should not be more than n. Right? If you ask for n elements, you might actually get less than n elements because the list might not be long enough. But one thing is for sure, whatever you do, you should never get more than n elements. So we could code that as a simple test. That would be to say that the length of that list should be less than or equal to n. So there's one possible test.
That's only if n is non-negative.
Well spotted. The property here, let me just see if I can actually compile it. So if I do QuickCheck, well, nothing will happen. Let me just see. Have I imported? Yep, I've imported QuickCheck. So if I do QuickCheck of prop of the take property, it fails pretty quickly, 5 tests, and the arguments that it failed on was -1 and empty. So if this is negative, the length of this thing will not be less than -1, for example. Can never be. So how do we fix that? We could take the absolute value. That would be a reasonable way to do it. Another way, so I think that's probably the best way to do it, but another way, which I'll use just to remind you of something we saw earlier, was this operator here, which is a way of filtering out tests, throwing away bad tests. They don't count towards the proper tests. It tries to do 100 tests, but only good tests are not bad ones. And we will say that if n is greater than or equal to 0, then we have a good test. Okay, so if n is greater than or equal to 0, then this is a good test, and it should come out to be true. So now when we try this, you'll see that it's discarding all the negative tests. It takes a little bit longer because it's throwing away a lot of tests. It passed 100 tests and it probably discarded roughly 100 negative values, as you would expect. Okay? Okay, a little bit more interesting then is connecting take and drop. Take and drop are they kind of belong together, right? They're sort of complementary functions. So what is a suitable property that relates take and drop? Any suggestions? Well, if you think about take is something which gives you the front bit of a list, and drop is something which gives you the rest of the list when you remove the front bit. So if you have a take of some number of things and a drop of some number of things, and then you join them together, you should get back to where you started with, right? Roughly. Okay? So if we have n and x's, and we could have a similar precondition here. If we take n things from x's, that's the front n elements, and we join that onto what we get by dropping n elements, then we should get back to where we started with. Okay, are we agreed on that? Okay, let's try it out. Okay, it's taking a little bit longer. Okay, that's very good. Now, one thing we didn't do in these tests is we didn't write in any types. So what does that mean? Well, it means that the interpreter is just working out the types for itself and leaving it at that. That's fine, but the types that the interpreter will work out will be polymorphic. How do you test polymorphic functions? Well, you can't provide polymorphic values in general. If I want to test the reverse function, I can't provide a value of some sort of polymorphic type. To actually perform a computation, I need a concrete instance. I have to decide, shall I test it for a list of ints, for a list of bools, for a list of bools, or whatever. And QuickCheck has to make the same choice. And QuickCheck makes a rather simple choice. It chooses the simplest type that it can think of. And we'll see that if we, oops, typing in the wrong window here. If we do a verbose check of the previous property, we'll actually see what cases are chosen. And what you see here is a list of blobs. So it's generating lists of blobs. What are blobs? Well, a blob is just an open and closed brackets. There's a lot of stuff about blobs, but basically what it is a data type defined to be itself. Again, it's a slightly syntactic sugar here because it's a symbolic data type name. That's the name of the data type, and that data type has a single constructor, right? So this is your void type. It's your unit. It's called unit in Haskell speak. It's a data type unit which has a single value unit. Okay, so it's kind of the most boring data type in the world. And it's also the simplest data type in the world, so that's the one that QuickCheck will choose if you give it a choice. Okay, so one way to force QuickCheck to choose a different value is to tell it to give the properties an explicit type signature. Another way, a slightly shorter way, is actually to insert a type constraint into the program. And you can do that anywhere in a program. You can say that a certain value has to have a certain type. And here's a trick, a slick way of doing it that I've seen. You write a where clause, a local definition, a dummy, this is a dummy variable, a dummy identifier called types. And here we want to say that the list that we want to test should have type. Let's say, what's a good type for testing this? What's the simplest type that will actually catch errors? If I'd, for example here, if I'd swapped take and drop, if I use blobs, and I might not really see the error. If you swap take and drop, then if your list only consists of blobs, it doesn't actually make any difference which order you join them in. So what's a simplest type that would actually catch that kind of error? You could use int. Could actually go even simpler than that, yeah? Bool. Bool is actually the simplest type that you need to test. There's actually an old theorem from Knuth. It's not expressed in terms of Haskell polymorphism, but basically it's the same thing. It says that if you have a sorting function, which is symbolic in the sense that it doesn't do anything which is specific to the data type that you're sorting, other than compare things, then if the definition works for Booleans, it will work for any type. That's kind of interesting. So here, a list of Booleans would certainly be the simplest thing we could use. So this is adding a type constraint. It's saying, oh, by the way, this thing must be a list of Booleans. And that way we can get it to test. So the first property, actually it doesn't matter because we're only interested in the length and not the elements in the list. Having a test involving these unit types is perfectly okay. We're only interested in the length of the list. But here we're interested in the equality between what we start with and what we get by joining these two things together. And for this case, we do actually want to test at a sensible type. Okay, I'll show you a little bit more about what you can do with QuickCheck and how you can observe what QuickCheck is actually doing when it's working, other than just by using verbose check. But I'll do that after we've had a break. Are there any quick questions before we take a break?
You need a test to see if it's a good test. Checking if n is greater than 0. Even if it's less, you should get.
Yeah, that's right. So in fact, in this one, it should work perfectly well. That's right. Let me just delete that. Yeah, working perfectly nicely. Yeah. Okay. All right, back in 15 minutes. So we were discussing testing properties of take and drop in this case. And this is an opportunity to tell you a little bit more about some of the things going on in QuickCheck. So you will be aware, of course, that this is a Boolean expression. And QuickCheck is able to check any Boolean valued function as long as it knows how to generate random values for that Boolean valued function. But in fact, by using this prefix here, we're doing something else. We're actually changing the type from Boolean to some other type that QuickCheck can test. And that type is called property. So QuickCheck can check Boolean valued functions. It can also check other kinds of functions, providing they give a property as their answer. So where do these property guys come from? Well, they're the result of using these special QuickCheck operations. This was a QuickCheck operation to tell QuickCheck, don't use any of the tests which fail this precondition. And so this operation here is not a Boolean operation, doesn't create a Boolean, but it creates a special QuickCheck kind of Boolean. So you can think of property as being like Booleans, but with extra stuff in to help and control QuickCheck. So we're going to use these things like QuickCheck. So I avoided having to talk about that earlier because I avoided writing down the types, and I even managed to avoid it down here. But the truth of the matter is, here's the type of prop take, because it uses a QuickCheck building block, a QuickCheck combinator, this guy here, then its answer is not Boolean, not bool, but property. Okay, but nothing to worry about. Just carry on using them as before for testing properties. But that brings me to the point where I'd like to show you at least one or two other Boolean, other QuickCheck building blocks. And they're building blocks that allow you to observe properties of the test cases that are being generated. What we saw was that we could use verbose check to see the test cases that were generated. But that's a lot of data, and it really doesn't necessarily help you very much. It's nice to do sometimes, but actually what you want to do is sometimes understand general properties of the data that's being generated. So one thing that the QuickCheck library provides are different ways of collecting and classifying data. So I'm going to show you a couple of those functions and how to use them here. So one of the things you might notice about this test is that we're generating a random number and a random list, and then we're doing a take and drop test. Now, if the number is less than or equal to 0 or bigger than the length of the list, then we're really only testing the extreme cases. In some ways, if I test this for -10 and I test it for -20, I mean, you're not really going to get any different information for those two answers. If I test it on a list of 5 elements with n being 1,000 or n being 10,000, all those tests are kind of much the same. They're a bit extreme. So I can actually sort of get some idea of how many of these extreme cases are being used by using the following. I can use a function called classify. And what am I going to classify? I'm going to classify anything which is where n is less than or equal to 0 or n is greater than the length of the list. I'm going to call such a case to be extreme. Not a very good word, but okay. So just look at the syntax here. What I'm doing is it's a bit like this operator here. It allowed me to put a filter in front of the test. This is allowing me to put some data collection in front of the test. So this will collect data and tell me what percentage of my test cases are in this so-called extreme class. So let's just compile that and let's have a test. So I have a QuickCheck somewhere. QuickCheck prop take drop. So now you see I passed 100 tests, but in fact 96% of them were in this extreme case, where I was either taking less than 0 or fewer elements, which are all the same, or I was taking more elements than they had in the length of the list. Okay? Now I'm not going to fix this problem today. I'm just going to draw your attention to it and show you that we have ways of seeing, of exploring what goes on when we do tests. So what we can learn from this is actually only 4% of the tests actually did interesting things within the range between 0 and the length of the list. And really they're the interesting cases for this take-drop example. So for the moment, we'll understand that we can observe, for example, by using the function classify, what goes on inside a test. What we don't know how to do yet, and what we'll see next week, is how we can get better control of our data test generation by using another part of the QuickCheck library, which is the library for building random distributions of data. That's something we will need to do in order to be able to test our own user-defined data types. But sometimes we need to do it as in cases like this, where we want to get a good representative range of values. Here we want to generate random values, a random list, and maybe then a number n, which is somewhere between 0 and the length of that list. At the moment, we don't have a good way of doing that, and so we don't get very good tests. Sometimes we will need to do that, and that's something we'll see next week. Okay, any questions? Okay, so classify is one of these ways of inspecting things. Another way of inspecting things is to collect. Let's collect. Let me see whether n is greater than So here I've done several things. I've added both a filter and a bit of collection, and I've collected the value of this Boolean expression. In fact, I could just collect the value of, yeah, let's take that example for now. Okay, and let's do a quick check of property for take. And you see us doing the test, it's discarding all these guys, and after having discarded them, it's going to collect this value and then give me statistics on that value, 93% true, 7% false. In other words, only 7% of the test cases did we have n less than the length of the list. Again, it shows you that tests are not very good. The random generation is not hitting the random values that we really think would make good tests. Nevertheless, the purpose of the example is really to introduce you to these other ways of observing QuickCheck tests.